College Algebra, Module 9, Topic 9.3, Exponential Functions and Models. Objective 1 is exponents. Let's review several rules that apply to exponents. Any number raised to the first power is itself. That means 5 to the first power is 5, or negative 3 to the first power is negative 3. Any non-zero number raised to the zero power is 1. Again, that means 5 to the zero power is 1, or negative 3 to the zero power is 1. But be careful, negative 3 to the zero power, that is the opposite of 3 to the zero power, which would give us negative 1. A negative exponent means reciprocal, that is, a to the negative n means 1 over a to the n. So if we have 4 to the negative 2, that means 1 over 4 to the second power. If the exponent is a fraction, the numerator of the power is the power, and the denominator of the power is the index. That is, a to the m over n power means the nth root of a to the m. Let's do some examples. Write the following using a positive exponent, then simplify if possible. Well, 9 to the negative 2 means 1 over 9 to the second power, but 9 to the second power is 81, so our answer would be 1 over 81. 9 to the zero power, anything to the zero power is 1. 9 to the 1/2 power, well, the 1/2 power means the square root of 9, which is 3. Negative 9 to the negative 3 over 2 power. Well, let's start with the negative power. That means 1 over negative 9 to the 3 over 2 power. Well, because the negative is not included in the parenthesis, that just means the negative is sitting out front making the answer negative. So we're going to have 1 over 9 to the 3/2 power. Well, a fraction exponent means the denominator of the power is the root, so it's the square root of 9. The numerator is the power, so we're going to simplify that and go the square root of 9 is 3. 3 to the third is 27, so our answer would be negative 1 over 27. Now, if we wanted to do these on our calculator, just to run through these real quickly, 9 to the power of negative 2, we need to go to math. Option number 1 writes it as a fraction, and we get 1 over 81. 9 to the power of 0 is just 1. 9 to the power of, remember, anytime we have a fractional power, we need to put the fractional power in parentheses, so we get 9 to the 1/2 power, which is 3. And then the last one would be negative 9 to the power of, then in parentheses, negative 3 divided by 2, which when we hit enter, we get our answer. So we'll go back to math, fraction, enter, and we get negative 1 over 27, which is what we had. Let's do a few more examples without using a calculator. 16 to the negative 1/4 power. Again, the negative power means 1 over, so that's 16 to the 1/4. Well, the 1/4 power is the same as the 4th root of 16, which means what number times itself 4 times would give us 16, which is 2, so our answer is 1/2. Negative 4 times 64 to the 1/2 power. Well, the order of operation says we do what's in parentheses first, but notice there's nothing to do in the parentheses. Then we do exponents, so 64 to the 1/2 power means the square root of 64, which is 8. So then we have negative 4 times 8, which is negative 32. And then the last one, 5 times negative 8 to the negative 2/3 power. Well, if we just do the negative 8 to the negative 2/3 power, that means 1 over negative 8 to the 2/3 power. Now notice on this one, the negative is included in the parentheses, which means it's part of the radicand, so it's the third root of negative 8 squared. Well, the third root of negative 8 means what times itself 3 times would give you negative 8, which is negative 2. So we're going to have negative 2 to the second power, which means negative 2 times negative 2, which is 4. So what we've got is 5 times 1/4, which gives us 5 over 4. Objective 2, exponential functions. Well, a function represented by f of x equals ca to the x, where a is greater than 0 and a is not equal to 1, and c is greater than 0, is an exponential function with a base a and coefficient c. Again, f of x equals ca to the x is our standard exponential function. If a is greater than 1, then f is an exponential growth function. If a is between 0 and 1, then f is an exponential decay function. Okay, the base, or the a part, has to be greater than 0. If it is a number greater than 1, it's growth. If it's a fraction between 0 and 1, that means it's getting smaller and smaller and smaller, and therefore that is a decay function. Just as a note, an exponential function has a variable for an exponent, whereas polynomial functions that we've been doing have constants for exponents. So 3 to the x is an exponential function, but x to the third is a polynomial function. Let's talk about exponential growth functions first. These are functions of the form f of x equals ca to the x with a greater than 1. So for example, f of x equals 3 times 2 to the x power. That is a growth function. If we were plugging points, if x is 0, then we get 3 times 2 to the 0. Well, 2 to the 0 is 1. 2 to the 1, 3 times 1 is 3. So if x is 0, y is 3, which is this first point on the graph. If we did another point, if x is 1, then we get 3 times 2 to the 1. So that's 3 times 2 is 6. So over 0 up 6, that is our second point on the graph. And then if x is 2, we would get 3 times 2 squared, which is 3 times 4, which is 12. Notice the graph is getting very high very quickly. So to talk about properties of an exponential growth function, the domain is from negative infinity to infinity, so the domain is for all real numbers. Remember, this is the value of x, so we could plug whatever we wanted in for x. The range is from 0 to infinity, meaning the output of a growth function is never going to be negative. The function increases on the entire interval from negative infinity to infinity, meaning there are no turning points. The negative x-axis is a horizontal asymptote, meaning the graph can get closer and closer to 0, but it's never going to actually cross over it. And the y-intercept is the ordered pair 0, c, which was what we found when we plugged x is 0. Now let's look at exponential decay functions. These are f of x equals ca to the x, where a is between 0 and 1. So this time we're going to look at the function f of x equals 3 times 1/2 to the x power, or 3 times 2 to the negative x. Well, again, If we plugged in x is 0, we would get 3 times 2 to the 0, which is just 3. So again, there's our ordered pair 0, 3. If x is 1, that's 3 times 1/2 to the 1, so that's going to be 3 over 2, or 1.5, which is halfway over here. And then if x is 2, we would get 3 times 1/2 to the second power, which is 3 times 1/4, which would be 3/4. So notice this time, as the x values get larger and larger, the y value is getting closer and closer to the x-axis. So the properties of an exponential growth function, where the a is between 0 and 1, domain is all real numbers. Again, the range is everything above 0. This time f decreases on the entire interval, and the positive x-axis is the horizontal asymptote, again meaning that is a line in which the graph never crosses that line. The y-intercept is 0c, which again is the ordered pair 0, 3. Objective 3, graphing exponential function. So let's say we wanted to graph the equation, or the function, f of x equals 2 to the x power. Well, we've got the general ideal of what our exponential function, it's either going to go like this or like this. So let's plug a few points to decide. So if x is 0, we get 2 to the 0. Well, anything to the 0 power is 1. If x is 1, we get 2 to the 1, which is 2. If x is 2, we get 2 to the second, which is 4. If we chose a negative x, we would get 2 to the negative 1, which is 1/2. If we plug negative 2, we'd get 2 to the negative 2, which is 1 over 2 squared, which is 1/4. So if we were going to graph those, over 0 up 1, that means c is 1. So that would be like 1 times 2 to the x. Over 1 up 2 would be over here. Over 2 up 4 is going to be doubled, so we're looking up here. If x is negative 1, then it's going to be halfway down there, and then it cuts halfway every time. So notice it's going to come through here and get closer and closer to the x-axis, but never hit it. If we wanted to do this on our calculator, we're going to go into y equals, do 2 to the power of x, graph it. There's our graph going through there. If we wanted to see the table, we could go second table, and that would show us different values of x. Objective 4, linear or exponential. To be a linear function, we are going to add a fixed amount to the previous value of y for each unit increase in x. An exponential function multiplies a fixed amount times the previous value of y for each unit increase in x. So let's look at this data. Is the data exponential or linear? Well, notice the x values increase by 1 every time. So the y values, and we'll come down here to the whole number. See, this one we increased by 3, this one we increased by 6, this one we increased by 12. Because we are not adding a fixed amount every time, it's not linear. So now we want to ask ourselves, is it exponential? Well, notice here we multiply by 2, we multiply by 2, we multiply by 2, or going backwards, divide by 2, divide by 2, divide by 2. Well, divide by 2 would give us 3 over 2 divided by 2. So because we are multiplying by 2 as the x's increase, this one is exponential. Okay, if it's exponential, find c and a so that c, a to the x models the data. Okay, so we're going to use some of our points here. Well, we know that f of 0 is equal to 3. So we're going to say f of 0 is 3 equals c, a, and we know that x is 0. Well, a to the 0 is 1. So we get 3 is equal to c times 1, or 3 is equal to c. So that's our first part. Then we're going to choose a different point. So I'm just going to choose this second point to find A. So we've got f of 1 is equal to ca to the 1. Well, we know that f of 1 is 6. We know that c is 3 times a to the 1. Well, that's just a. Divide by 3, divide by 3. So we get a equals 2, which we knew because that was the amount that we multiplied by every time. So our function is going to be f of x equals 3 times 2 to the x. That is the exponential function that models this data. And I'll show you in a little while how to do this on your calculator. So for the next example, find a linear or exponential function that models the data in the table. Well, again, notice the x values increase by 1 every time. Notice that the y values we get decrease by 2, decrease by 2, decrease by 2, decrease by 2. This one is going to be linear because we are adding a negative 2 every time. So do you remember our linear function f of x equals mx plus b? B is the y-intercept, which means it's the y value when x is 0. So b is equal to 3. The slope is the amount of change of y's based on x's, so our slope is going to be negative 2. So our linear function is going to be f of x equals negative 2x plus 3. And again, you could do your linear regression on your calculator to find this linear equation. Another example. Find c and a so that f of x equals ca to the x satisfies the given conditions. That is, f of 0 equals 7 and f of negative 1 is equal to 1. So we're going to start out with f of x equals ca to the x, and we're going to plug in x is 0. So we get f of 0 equals ca to the 0. Well, f of 0 is 7. ca to the 0, a to the 0 is 1. So basically we've got that c is equal to 7. Then we're going to take that and we're going to do it again. This time we're going to do f of negative 1 equals ca to the negative 1. Well, f of negative 1, they just told us was 1. c is 7 times a to the negative 1. That means 1 is equal to 7 times 1 over a. 1 is equal to 7 over a. So to solve for this, we're going to multiply both sides by a. So we get a is equal to 7. So for this problem, we get f of x is equal to 7 times 7 to the power of x. Now in application, the pressure in the tire with a leak is 30 pounds per square inch initially and can be modeled by f of x equals 30 times 0.09 to the x after x minutes. What is the tire's pressure after 9.5 minutes? Well, they give us the formula that calculates the pressure where x is given in minutes. So all we're going to do, because we're trying to find the pressure for 9.5 minutes, is we're going to go 30 times 0.9 to the power of 9.5. Now when we do this, we're going to need our calculator. So we're going to type in 30 times 0.09, close the parenthesis, to the power of 9.5. And that gives us 3.48678 times 10 to the negative 9th. But remember, 10 to the negative 9th means we're going to move the decimal back 9 places. So it would be 0.000000349 or 34868, depending on what they want us to round to. Now let's do an application involving our calculator and regression. The table lists the concentration in a sample of E. coli bacteria B in billions per liter after X hours. Find the values for C and A so that CA to the X models these data. And then B part says estimate the bacteria concentration after 6.2 hours. Well, pull out our calculator, go into Stat, and we are going to edit. Then we're going to enter the X values in L1, and then we're going to enter the B values in L2. Once we get our values stored in our list, then we're going to go to Stat, Calc. Now so far we've done linear and quadratic and probably cubic. This time we're going to go down to number 0, which is exponential regression. Press enter, then press enter again, and we get y equals AB to the X. What's different about this is that our typical formula is CA to the X, but this calculator shows AB to the X. So when they are asking you for C, your calculator is showing that as A. So your C is your constant, which is 0.4996, or we'll just call that 0.5. And then your A value, well, that is actually the B on the calculator, which is 2.32. So our function is going to be f of x equals 0.5 times 2.32 to the x. And then B part says estimate the bacteria concentration after 6.2 hours. Well, what we're going to do is we're going to take the formula that we just found, and we are going to find f of 6.2, which means we're going to take 0.5 times 2.32 to the 6.2 power, and that will give us 92.3 in billions per liter. Now see, this would make sense because 6.2 would be between 5 and 8 on our values, which means our B values is going to be between 93 and 414. So that's how we do the regression, just like we have been doing it, except this time we're going down to exponential. Objective 5, the value of E. The value of E is the limit of 1 plus 1 over n to the n as n goes to infinity. Now this sort of reminds me of pi, because they didn't just pull the value of E out of the hat. When they look at this limit, if n is 1, then you get 1 plus 1 over 1 to the power of 1, which is 2. If n is 10, we get 1 plus 1 over 10 to the 10th power, which is approximately 2.59374, and so forth. So this chart just shows you that as n gets really large, notice this value is about 2.718. Well, that is the value of E. Now, E is an irrational number. It never ends. It never repeats. And that's why it reminds me of pi, because we'll talk about it as being 2.718, although it goes forever and ever. Now, when you're doing this on your calculator, on these calculators, you can, if you just want E, it's right above the division symbol in yellow, so you can do second E, press enter, there's your 2.718. Or if you know you're going to have to take E to a power, you can use the E that's right above the natural log, so that would be second E to the power of, if we just chose 1, then again we get our 2.7182. Okay, let's do some examples. E to the 1.5. Well, we're going to have our calculator for this, so I'm just going to go to second natural log, which is e to the power of 1.5, which gives us an answer of 4.481. So when we round to the nearest hundredth, we get 4.48. Okay, let's do another one. E to the power of negative 3.3. Again, we'll go second natural log, which is e to the power of negative 3.3. which gives us rounded to the nearest hundredth 0.04. Now for these examples, we want to evaluate f of x for the given value of x. That's still the same thing though. F of 2.3 means we're going to go into our function everywhere there was an x. We're going to plug in 2.3, so we get e to the power of 2.3, which gives us 9.974. Again, if we rounded to the nearest hundredth, we would get 9.97. Objective 6, compound interest formula. If P dollars is deposited in an account paying an annual rate of interest R, compounded n times per year, then after T years the account will contain A dollars, where A is given by the formula P times 1 plus R over N to the power of NT. If the interest is compounded annually, meaning they're only going to do this once per year, then N is 1 and we get A equals P times 1 plus R to the power of T. Now when we talk about the compounding periods, the N on the previous formula, A equals P times 1 plus R over N to the NT. N is the number of times per year they're going to compound it. So if it's annually, which means N is 1, that means they're going to do it one time per year. Semi-annually means they're going to compound it 2 times per year, so N is 2. Quarterly, N is 4. Monthly, 12 times per year, N is 12. Or daily, N is going to be 365. So let's do some examples. Find the amount of money in an account if $2,000 is invested at 4% compounded annually for 5 years. So for this problem, the rate is 4%, or as a decimal is 0.04. It's compounded annually, so N is 1. P is the amount of money invested, or the principal, which is $2,000. And T is the time in years, which is 5. So our formula, A equals P times 1 plus R over N to the NT, because it's annual, becomes P times 1 plus R to the T. So we would get 2,000 times 1 plus 0.04 to the 5th power. Or we could even call that 2,000 times 1.04 to the 5th power. At this point we're going to need our calculator. So we get 2,000 times 1.04 to the power of 5. So at the end of 5 years, this account would have $2,433.31. For the next example, find the final amount if $2,000 is invested in an account paying 4% and we're compounding it quarterly for 5 years. Well, R again is 0.04. This time, because it's quarterly, that's 4 times a year, so N is 4. P is still $2,000 and T is 5. Now this time we're going to use the big formula, so we would get A equals 2,000 times 1 plus 0.04 divided by 4 to the power of, it's the number of times per year times the number of years, which is going to be 20. So we would get 2,000 times 1 plus 0.04 divided by 4 to the power of 20. So when we type this in, we're going to get 2,000 times 1 plus 0.04 divided by 4, close the parenthesis, to the power of 20, which would give us $2,440.38. Now the natural exponential function f of x equals e to the x is used for continuous compounding and growth applications. The continuous compounding formula is A equals PE to the RT. Sometimes we'll call that the PERT formula, where P is the principal or the initial amount, R is the annual interest or growth rate written as a decimal, and T is the number of years. So what this means is instead of them compounding once a year or twice a year or 4 times a year or 365 days a year, they are compounding it continuously. They'll calculate the investment and then they'll do it again and again. So it's just automatic compounding and they never stop. So for this problem, R is 0.05, which is our 5%. P is our principal, or $7,000. We're compounding for 10 years, so T is 10. And we're going to use our PERT formula. So when we substitute in, we get 7,000 times E to the power of 0.05 times 10. Now when we do this on our calculator, we need to watch out because we've got 7,000 times E, which is our second E to the power of the 0.05 times 10 needs to go in the parentheses together. Because if you close that parenthesis, it's going to do 7,000 E to the 0.05, get an answer, and then multiply that by 10. So make sure that your RT goes together in the parentheses, which gives us a total amount of $1,541.05. Now it doesn't tell us to round to the nearest hundredth, but because we're dealing with money, we always round to 2 decimal places. Another application. Suppose the amount of a radioactive element remaining in a sample of 100 milligrams after X years can be described by the function A of X equals 100 E to the negative 0.01283x power. How much is remaining after 296 years? Well, the formula talks about the amount of the radioactive element remaining. X is the number of years. So for our problem, we are just going to go A of 296 is 100 E to the negative 0.01283 times 296, which would give us on our calculator, and we get 2.24. The amount of radioactive materials remaining would be 2.24 milligrams. Another application. The population of Phoenix, Arizona in 2000 was 1.3 million and growing continuously at a 3% rate. Assuming this trend continues, estimate the population of Phoenix in the year 2010. Well, we're going to do our A equals PE to the RT. Because it's continuous, we know it's E. So our P is our original amount, which is 1.3 million, times E to the rate is 0.03 times time. Well, we're going for 10 years. So we're going to need our calculator. 1.3 times E to the power of 0.03 times 10, which gives us 1.7548. So this means if the trend continues, then the population of Phoenix in the year 2010 will be about 1.75 million people. You are now ready to do the homework for topic 9.3 in my math lab. Once you complete all 3 sections with a score of at least 90%, you will be ready to take the Module 9 quiz. And as always, if you have any questions, let us know.